We're going to start with polar coordinates.
We're not going to do that much with polar coordinates. They're kind of fun. In a different class, we could spend a week doing interesting stuff. But it mostly has to do with leading up to something that's even more fun than polar coordinates. So, what are polar coordinates? Well, the coordinate system we're used to is called the Cartesian coordinate plane. It's the XY plane. And each point on the plane has an X coordinate and a Y coordinate. There are actually many ways to describe a point on a plane using different coordinate systems. This polar coordinates, what we do is we draw a line to the point, and relative to the x-axis we have an angle. And the distance from the origin to this point we'll call the radius, or r. So now we can describe the same point in terms of an r and a theta. So same amount of information, but different information to describe a point. As a side note, if you have a graphing calculator and you go into the mode, you'll see that one of the options is the pole mode, POL for polar, and so you can enter polar equations and see what the graphs look like. Right, so there are some important differences. One of the most significant differences is that polar coordinates are not unique. That is to say, if I have a point 3, 0, that would be, say, out here, I can describe that as 3, 0, 3 the distance, 0 the angle. But I also could describe it as 3, 2 pi, or 4 pi, or 6 pi. So something to keep in mind that these coordinates are not unique. In the case of the origin, right, we describe the origin as having a 0 distance. And then the angle can really be anything. So it's significantly not unique. I just made that phrase up. I don't know if it makes any sense.
So are you saying that like it doesn't really matter what angle you have?
Yeah, like 0 and 1 degree is the same as 0 and 2 degrees, as 5,000 degrees. Any number you want to plug in here, or 0 degrees. So it's something different. Okay, so one of the things we need to be able to do is we need to be able to convert back and forth between polar and Cartesian coordinates. And this is not a big jump at this point because of all our background in trigonometry. If I fill in here, here's my here's my y distance, and here's my x distance. It becomes pretty clear right away that that x is r times the cosine of theta, and y is r times the sine of theta. So, given a set of polar coordinates, it's very easy to convert them back to xy Cartesian coordinates. Just take a simple example. I have the polar coordinates 4 and 2 pi over 3. So my x would be 4 times the cosine of 2 pi over 3, and y would be 4 times the sine of 2 pi over 3. Well, you might have to think a little bit about what the sine and cosine of 2 pi over 3 is. That's in the second quadrant, and its reference angle is pi over 3. Didn't draw that very nicely, so I guess it's a 60-degree angle. Okay, so the cosine of 60 degrees, that's going to be a half. So 4 times a half. And y is going to be 4 times, wait a minute though, cosine over here is going to be minus, so negative a half. So it's going to be negative 2. And the y coordinate is going to be 4 times the sine of pi over 3, which is square root of 3 over 2, or 2 times the square root of 3. So this is equivalent to minus 2 square root of 3. All right. So that's how you convert in one direction. Converting in the other direction is pretty simple, but not quite as straightforward. We can see, since this is a right triangle, using the Pythagorean theorem, we can see right away that r squared equals x squared plus y squared. So r is the square root of x squared plus y squared. However, we can see also that theta will be the inverse tangent or arctangent of y over x. But that creates some confusion here. We have to be careful now. In the first quadrant, it will be the positive value. In the second quadrant, it'll be negative. In the third quadrant, positive again. And in the fourth quadrant, negative. So we have to be able to figure out which quadrant theta is in, right? Well, if we have x and y and we look at their signs, we can always figure that out. I mean, if they're plus plus, it's obviously the first quadrant. Minus minus, the second quadrant. Minus plus, they'll be the third quadrant. Minus plus will be the second quadrant, and of course, plus minus the fourth quadrant. So if I get some value out of this, say I get pi over 3, but looking at the signs in the fourth quadrant, then I know it's going to be this angle down here, which is not pi over 3, it's going to be, is that going to be, it's 5 pi over 3. A note for any of you who are computer science bound, your computer science language, they don't have an inverse tangent function. Put in some x and you get the value out that you would get out of your calculator. But There will also be a function usually called ham2, where you put in the x and y values. It looks at them and it gives you the correct angle. You don't have to adjust for which quadrants might be in. All right, so here's our conversion, more or less. You know, I guess asterisk here. We might have to adjust theta. I guess we should take a look at an example of this also. I wanted to convert the Cartesian coordinates to -2 to polar. Well, my r is going to be the square root of 2 squared plus -2 squared. That's going to be 2 square root of 2. Theta is going to be the inverse tangent -1. Well, that's 3 pi over 4. But it would only be 3 pi over 4 if it was in the second quadrant, right? Minus plus, but it's not, it's a plus minus. So it actually has to be not this angle, but an angle down here in the fourth quadrant. So it's either, you could call it minus pi over 4, or you could call it 7 pi over 4. So the polar coordinates are 2 square root of 2, 7 pi over 4. So that's how you would convert back. All right, we're not going to do much else with polar coordinates in this mode, but as I said, they're kind of fun, and I want to at least show you a little bit about what I mean by that. This is Grapher, comes with Max. I think you can do the same thing on a Desmos. You can certainly do something similar on your TI-80. Let's just take a simple equation. R equals 4. Fit it on the screen. R equals 3. Okay, so if you just, this is a polar equation. If I just say the radius is 3, I get a circle. Okay, that's nothing real surprising there. If, however, I say R equals cosine of theta, make that a little bigger, you also get a circle. So now, instead of centered in the center at the origin, it's now centered off from the origin. Okay, that's kind of simple. I guess we should wonder here, what if I say 3 is the sine of theta? Okay, that's a circle too, but now it's oriented a little differently. What if I were to add something to this function? Now there's something, let's move it over. A little more interesting. This, I believe, is called a cartoid. Cartoid. C-A-R-T-O-I-D, because it's heart-shaped. There are other things you could do. We could say R r equals, let's see, theta divided by 10. Okay. Make it a little bigger. Unfortunately, this graphing program is just stopping here. It's not continuing, but this is a spiral. It's exponential spiral, I believe. There's kind of a historical little controversy involved with this. I think there's a famous mathematician who came up with this exponential spiral, and they put it on his gravestone. But they didn't put an exponential spiral. They put a different kind of spiral. Which I have to notes on it. Okay. All right. So one last thing you can create overleaves, kind of things here. And a spirograph. Never heard of spirograph? Okay. It's a toy from the 60s. Draw things like this. All right, so there's fun stuff you can do with polar coordinates if you're artistically inclined. But I'm gonna leave it there for now. We're gonna use polar coordinates to do something I think is just really cool, just really dramatic. It's going to take a few minutes of work here, but it just going to show you that you kind of have a sense of the way numbers work, right? You add numbers, you multiply them, you divide them, you get another number. You multiply two big numbers, you get a bigger number, all that kind of stuff. But when it comes to complex numbers, there's some funny business that is, again, once you see it, you go, oh, that's interesting. All right, so forward. So when we think of complex numbers, we often think of, again, a plane. Now it's not an XY plane, where we had the X coordinate, we have the real numbers, and where we had the Y, we have imaginary numbers. And we think of a complex number as some point here. Let's give it coordinates A and B. And we think of, just traditionally we'll use Z as meaning, I mean a complex number, as opposed to X and Y, where I probably mean a real number. So this point represents A plus BI. And I want to say one more thing about complex numbers. I don't know if we talked about this, but if we have Z, we have a complex conjugate, which I'm going to write as Z asterisk, which is A minus BI. And one nice thing about the complex conjugate is if I multiply Z times its complex conjugate, I get A squared plus B squared, which of course is a real number. And having done that, I want to define something. I'm going to define this symbol here, which you might think of as absolute value, but that doesn't really make sense when you're talking about a complex number. We call this the modulus of z. We define that as the square root of z asterisk, or the square root of a squared plus b squared. No, done complex numbers before, you might be familiar with these terms. And this is called this the modulus. Okay, so again, we map this out, this complex number, as a kind of on a Cartesian coordinate system, even though we're not talking about x and y. We could, however, use polar coordinates. So again, we're going to have an angle here, theta, and a distance from the origin to the point, which is r. But now, since r is the square root of a squared plus b squared, we can also write it as the modulus. Let's write RZ in terms of this R. Specifically, I want to factor R out of my A plus BI. Well, I can do that by multiplying by R and dividing by R. And now if I look at this, and I look at my diagram, I can see that A over R, right, that's the cosine of theta. And B over R is the sine of theta. So there's pi in there. That is to say, I can rewrite my A plus BI complex number in terms of R and theta. R times the cosine of theta plus I sine of theta. This is the polar version of a complex number, the polar form. All right, well, let's actually use a real example to see how we would actually make this conversion. My z is, say, 3 plus 4i. So the first thing to do is to figure out what r is. Right? R is the modulus of z. It's the square root of 3 plus 4i times 3 minus 4i, which is the square root of 3 squared plus 4 squared, which, if you remember your 3, 4, 5 right triangles, this just has to be 5. Okay, let's rewrite z as r, 5 times 3/5 plus 4/5, 5. Well, now we want to find out what theta is. Okay. Well, we have an x and a y here. So theta is our inverse tangent of y over x, which is 4/5 over 3/5, which is inverse tangent of 4/3. And in radians, that's approximately 0.927. So again, we can rewrite z as 5 times the cosine of 0.927 plus I times the sine of 0.927. Converting back from this form to z is pretty obvious. You just evaluate the cosine and multiply by the radius, evaluate the sine and multiply by the radius. So I'm not even going to do that. All right. This is actually a lot. So if you need me to slow down here, have a question, or you need a minute to let this sink in. Again, we're just looking at complex numbers in a different way. And there are going to be some surprising results that are going to come out of this. All right. Surprising result one takes a little algebra. What we want to do is we want to take two complex numbers in polar form and multiply them and see what happens. So we have R1 theta 1, and we want to multiply that by R2 theta 2. So let's see how that works. R1 is R1 cosine theta 1 plus I sine theta 1 times R2 cosine theta 2 plus I sine theta 2. I'm going to FOIL these. The R's, they come out front. That's nice. We get cosine theta 1 cosine theta 2 I guess I'm going to do the firsts and the lasts. This is the first. The lasts are I sine theta 1, I sine theta 2, but the i's become minus 1, so minus sine theta 1 sine theta 2. And then what do we have? We have I times sine theta 1 cosine theta 2 plus I sine theta 2 cosine theta 1. Okay. But this ugly thing is going to collapse very nicely. Take a look here. Cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. That should trigger something. Cosine x plus y is cosine x cosine y minus sine x sine y. This is just cosine of theta 1 plus theta 2. Okay. Over here, if we take our I out, what do we have? Sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2. That's just I times sine of theta 1 plus theta 2. Oh. Okay, that tells us something really interesting about multiplying two complex numbers in polar form. The moduli, the radius, well, we just multiply those. That's not a surprise. But the angles, we just add the angles. I have to kind of draw something here. Kind of illustrate that. Say I have say this is my unit circle, right? And and I have, say, a 30-degree angle here. This is the complex plane, so I have a point here. And let's say at 60 degrees, say my radius is 2. So to multiply these, well, I multiply these lengths, so that's just going to be 2. But what happens to the angle? I just add 30 degrees and 60 degrees and I get 90 degrees. So that tells me the product of these two complex numbers has to be this. That's kind of weird, you know. If I was just dealing with numbers whose moduli is 1, right? I'm just dealing with angles whose complex numbers are on the unit circle, I'm just like, just add these angles and I get a new point. So I can move around the circle as much as I want. All right, there's an equivalent formula if I want to divide these two numbers. I think it's pretty one. I wanted to divide R1 theta 1 by R2 theta 2. It's just going to be R1 over R2 times cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2. In other words, when I multiply, I'm going to add the angles. If I want to divide, I'm going to subtract the angles. All right. Let's actually do a real example of this. So my first complex number is in polar form 2 cosine pi over 4 plus I sine pi over 4. And my second is 5 times cosine pi over 3 plus I sine pi over 3. And I want to multiply them. Well, 2 times 5 is 10. And then I'm going to get the cosine of pi over 4 plus pi over 3. Let's see what that is. That's what? 3 pi over 12 plus 4 pi over 12. 7 pi over 12 plus I sine 7 pi over 12. I want to think for a second now. This is going to come up in a bit. At least part of this operation here, instead of I'm trying to multiply two quantities, but I end up adding quantity. Does that sound like anything familiar? Is there any circumstance when we want to multiply two things, but we end up adding? Yeah, sounds a lot like exponents. There's a connection that will be coming. Okay, let's push this multiplication formula a little further. Say I have some complex number, r cosine theta plus I sine theta. I want to square it, right? Well, that's really easy now, right? It's just going to be r squared cosine of theta plus theta is 2 theta. Okay. Oh. I go to 3, doesn't really change much, right? It just becomes 3 theta plus I sine 3 theta. So anyone here remember what proof by induction is? We can skip that. But proof by induction is useful when you want to show something that's maybe it's true for 1 or 2 or 3. You want to show it's true for any n. You start by an anchor where you show it's true for 1, and then you show if it's true for n, it's true for n plus 1. So here if I say z sub n is equal to r to the n times cosine n theta plus I sine n theta, and now I just multiply this by z, so that's r cosine theta plus I sine theta. Well, that's r to the n plus 1 times cosine n plus 1 theta plus I sine. It's kind of a trivial proof here, plus 1 theta. Aha, but that's just, that's just z to the n plus 1. So it's true for all n. Right? So let's write that down. We have z to the n is r to the n times cosine n theta plus I sine n theta. I'm going to do a little bit of hand waving here. Using this formula, I know that if I have this expression, r to the 1 over n, that's the nth root of r, times the cosine of theta over n plus I sine of theta over n. And if I were to raise that to the nth power, in other words, this is z, and I'm raising it to the nth power, this formula tells me I would get r times cosine of theta plus I sine theta. But then, if I take the nth root of both sides, right, I raise each of these to the 1 over n. Well, this is z, so that tells me z to the 1 over n is just what I started with here. So that tells me this formula is not just good for integers, it's also good for fractions, and it's a fraction. We could go one step further and say, well, if it's true for n integers and fractions, how about for all real numbers? That's kind of an involved proof that it's kind of above my pay grade right now, so we're going to skip that. We're just going to assume that's the case. Okay, this is a wonderful formula, and it has a name. This is called, better get it spelled right. Math's theorem. This is actually really useful. I just want to give you an example of how it, a real-world example. What if I had this complex number? And what I wanted to find was, I'm going to find this to the 10th. Well, I know how to multiply complex numbers, so I could spend a lot of time doing this multiplication. But De Moivre's theorem gives me kind of an end run here. To do that, I first have to put this into polar form, so let me go ahead and do that. The modulus here is the square root of 1/2 squared plus 1/2 squared. So that's 1/4 plus 1/4. Square root is 1 over the square root of 2. And theta is the inverse tangent of 1. So that's going to be pi over 4. So we can rewrite this as 1 over the square root of 2 times the cosine of pi over 4 plus I sine of pi over 4. And now I want to raise this all to the 10th power. Well, De Moivre's theorem makes this very easy. This is just going to be 1 over the square root of 2 to the 10th times the cosine of 10 pi over 4 plus I sine of 10 pi over 4. This would be harder if this was not an even number. But 1 over the square root of 2 to the 10th is just 1 over 2 to the 5th. 2 to the 5th is 32. Cosine of 10 pi over 4. Well, 10 pi over 4, that's 2 and 2/4. You can get rid of the 2, so it's just cosine of pi over 2 plus I sine of pi over 2. All right, what's the cosine of pi over 2? 0. Sine of pi over 2 is 1, so this is just 32i. So we saved a lot of time there, right? We didn't have to do this multiplication out. All right, well that's one neat thing you can do. But going in the other direction, in a way it's even better. I mean, what if I wanted to know what the 6th root of -1 is? And let me rewrite this a little differently. What I'm really interested in is if x to the 6th equals -1, how many roots is that going to have? 6, yeah. But go find them, right? And that's not going to be too easy. Well, let's see how De Moivre's theorem can help us there. -1 is -1 plus 0i, right? So the modulus is just 1. right. So now I want to know what theta is going to be. Well, I just draw my unit circle here. So it's this point here, right? -1, 0. That's the cosine of pi plus I sine of pi. So that we get to the right answer, of all the right answers, I'm going to rewrite this. I think you'll agree that, oh, well, this is z, I'm sorry, it's not the modulus, this is the modulus of z. Z equals cosine of pi plus 2 pi n plus I sine of pi plus 2 pi n. Going to need that. So z to the 1/6, that's just going to be 1 to the 1/6, right? Plus, well, times cosine of pi plus 2 pi n over 6 plus I, put that bracket here, did I? Pi plus 2 pi n over 6. Okay. I'm going to need some room for this. So one of the solutions is cosine of pi over 6 plus I sine of pi over 6. We'll investigate that a little later. If n is 1, that's 3 pi over 6. That's pi over 2. Right. This is 2. That becomes 5 pi over 6. And what else? 7 pi over 6. 7 pi over 6. 2, 4. Did I miss one? No, that's not right. 3 would be, 2 would be 5. 1, 3, 5, 7 pi over 6. And then 9 pi over 6 is 3 pi over 2. And finally 11 pi over 6. Okay, let's do the easy ones first. What's the cosine of pi over 2? 0. And the sine of pi over 2? 1. So this is just I. Right? I is one of the 6 roots. How about 3 pi over 2? The cosine of 3 pi over 2, it's 0 again, but the sine is negative. So it's negative I. Okay? Yeah, negative I. Okay, pi over 6 and sine of pi over 6. I have to draw myself a little triangle here. The cosine is going to be square root of 3 over 2, and the sine is going to be a half, so 1/2 I. 5 pi over 6 is the same, except that the cosine will be negative. Uh, 7 pi over 6, that's in the third quadrant, so negative negative square root of 3 over 2. These all have the same reference angle, right? So all these numbers are going to be the same. And finally, square root of 3 over 2 minus I minus 1/2 I. Okay. So we got 1, 2, 3, 4, 5, 6. This is something we couldn't do before, right? I mean, how would we, if I said, what's the 5th root of, I don't know, I plus 7 or something? I have no idea. But here we can just use Demoivre's theorem, and we can find this out. So I think it's pretty amazing here, right? We just added a little trigonometry to our understanding of complex numbers, and now we can do a lot more. Yes?
Could you use those as kind of in terms of like x and y and write this actual root stuff and the actual equation for it?
If you plug any of these numbers into this equation, you get -1 equals -1. So, if you're presented with, I don't know, x to the 5th equals 2 plus I, right? This is how you can figure that out. Right? Or if, I don't know, I guess you might have just a quadratic. You might have, say, x squared plus x plus 1 plus I, right? So let's use the quadratic, right? -1 plus or minus the square root of 1 minus 4 times 1 plus I all over 2. So -1 plus or minus square root of -4 minus 3 minus 4I over 2. Right? Can I find the square root of -3 minus 4I? Yeah, I can. But I have to go through this process. Well, that will be all for today. Any questions or? Okay. There's a new homework assignment listed. It's the last homework assignment. You can turn it in. It's due technically on the last day of class, but you can turn it in at the final or we're not